Our next topic is momentum. So this is going to be a complete change of gears, completely unrelated topic in some ways to what we're just talking about. Although with energy is of course an important topic, and now that we've kind of cracked that open, we'll commonly refer back to it on occasion. So momentum, we're back to vector land. So if you were hoping we were done with vectors, vector components, all that stuff, then unfortunately that's something that we never really get away from. And momentum is lowercase p vector, no relationship to power, which is uppercase p, and it's not a vector. And the way that we form the momentum of something is to take its mass and multiply by the velocity. So I have an object that has a mass, it has some state of motion, and the momentum vector is basically just packaging them up into a single value. I like to call it velocity enhanced. It's like an extra piece of information. It's the state of motion times the mass that's in that motion. It creates a new vector, which is exactly in the same direction as the velocity, but of course multiplying it by mass means that it may not necessarily be the same number nor the same units. In fact, of course, this is going to be different units. Let's take a moment to just do a little bit of a units guide. The units of momentum would be, what's the units of mass again? Kilograms. Velocity?
Meters per second.
Meters per second. So the units of momentum are kilogram meters per second. At this stage, we might come up with an abbreviation, but we don't. There is no abbreviation for this. I don't know why. Maybe it's just barely simple enough that it's not too much of a pain to just write. My guess is probably more that Newton came up with all this stuff, so Newton already has a unit. Okay. Let's compare and contrast with some other units. Force. That's another vector quantity, right? So these were both vectors. So force is mass times acceleration, right? Newton's first law, Newton's second law. That's a mass times acceleration, kilogram meters per second squared. That did get an abbreviation. What do we call that? A Newton. If you notice, the only difference between those two is an extra second in the denominator, right? So we could, if we wanted to, write momentum as newtons times a second, right? Because then if we multiply it by a second, we'll get that square out of the denominator, right? We'll find that there is a good reason why the units of momentum happen to come out to be newtons seconds. It's not just an accounting trick. There is some relationship between force, time, and momentum. While we're at it, let's take a look at some other units. We discovered work and energy. Units for that are force times displacement, right? So that'll be kilogram meters squared per second squared, or Newton meters. That got an abbreviation too. What was that called?
Joule.
It was a joule, right? So you can see that it seems like every permutation of kilograms and meters at the top and seconds down below, right? In fact, what would be left? Kilograms up top, that seems to be the common thread. And then we have to take a turn with meters square being up top and just seconds being below, right? Just to kind of close the loop, right? So I think that's every permutation of meters squared in the top, and seconds squared at the bottom. You might ask, what is this? It is something It's called angular momentum, and we're going to talk about it much later in the course, but if you're thinking that there's one missing at this stage, then of course we should probably mention it. That's also a vector. And of course, these guys are scalars. They're just numbers. So that's just a little aside on units, a review of some stuff we already have seen. It doesn't hurt to remind you what a newton or a joule is, and a little sense of where we are going. But the next thing I need to do is to prove to you that momentum has any usefulness. This is not just a new torture device, another quantity to have you have to learn for no reason. For instance, when we developed the ideas of work and energy, hopefully it was impressed upon you in this current homework how incredibly easy it makes certain calculations to do. Momentum, same thing. It'll take things that were much harder to do before and make them much easier. In fact, it's going to turn out that momentum in some ways is just as fundamental as velocity itself. And so that's what I aim to show you next. So we go back to something Newton's second law. F net equals ma. It's been the cornerstone of the class so far, right? It allows you to relate the pokes and prods on an object from its environment, which we combine into what's called F net, and allows you to relate to how the object reacts to those pokes and prods, the acceleration. Of course, the third ingredient is the mass, which is a measure of how stubborn the object is to changes. That has been the cornerstone of the class so far. It, of course, was the central thing in the force method, and that, if you remember, also got slotted into our derivation of the work-energy theorem. So the work-energy theorem is based around it too. So all of our ideas so far have been based around this law. What I'm about to tell you is that this is not really the law. You can express this law more fundamentally, and indispensable to it is momentum. The full, most general form of Newton's second law is this. And you can see that momentum is right there, front and center. So the net force on an object will change its momentum over time. The net force on an object changes its momentum with time. That's really Newton's second law. So then, of course, you might well ask, if that's really Newton's second law, where do we get off using F net equals ma? Let's take a look. I'll substitute in momentum. Momentum is mv. Now, this is the first time we've had not one but two variables inside the delta, so we should probably talk about what that means. What does delta mv mean? Well, it means m final v final minus m initial v initial. That's what it means. So anytime you have a delta around anything, it's just indicating it's a change, final minus initial. Now, if the mass of an object is constant, then of course m final and m initial are one and the same mass, and we can factor that out. There's no reason to talk about m final and m initial as separate things if they're one and the same. So this gives us m times delta v. So this step is true if the mass is constant. Basically, that's a kind of an important thing to know about delta math, is that if anything in the sign of the delta isn't actually delta-ing, changing, then take it out. You can take it out. this is what? Acceleration. So there we get our old friend F net equals ma, right? But notice that to get to F net equals ma, we had to make an assumption that the mass of the object was constant. That is not always true. For instance, if you have a rocket ship that is burning fuel and sending it out the back, it is getting less massive. So there are systems where the mass of the system is changing with time. And if that's the case, you have to use the original form of the law, not this special case version that we always use, which assumes that the mass of the object is staying put throughout the problem. Okay? So, hopefully that's impressing upon you how fundamental momentum actually is. Okay? If you want to express Newton's second law in its most fundamental form, you need momentum. Now we're not going to do problems where the mass changes. Okay? That's something that is going to be a little too advanced for us. We're not going to do that rocket ship problem. Maybe you'll do it in the supplement. How many people here are in the supplement, by the way? Just curious. In the Physics 211 supplement? Oh, okay, no one. That's all right. So we still have to find some kind of usefulness for momentum calculationally that we didn't have before, right? Right now we don't have anything else than F net equals ma, which we already kind of knew. So my next goal is to show you when momentum is useful. So when is momentum useful in terms of being the easiest way to tackle a problem? So here's what I'm going to do. I'm going to set up a surface. And by the way, you'll do this next week in your lab. It is going to be a horizontal, frictionless surface. This is going to be our playing field. How do you make sure it's horizontal? Well, in your lab, you take a level and you try to make sure it's as level as possible. How do you make it frictionless? Well, that's easy to do here on the board because we just pretend. How do you actually make a frictionless track in your lab? You can't. That's impossible. Instead, we have these the objects that are on the surface be on wheels. We'll learn later in the course that if you're on wheels, then you can roll a lot more freely than if you were sliding. In fact, it approximates frictionless behavior. So, what do we have going on this surface? We're going to have two objects that are going to be sliding towards each other on a collision course. So I'm going to call this the initial step. I'll draw a little snippet of them colliding. So, like this. They're colliding. I'll call that the during the collision. And then I will take a look at the final, which is after the collision. Now, I should mention that there are many outcomes to this collision that depend on the details of how massive they are and how fast they're going initially. They could both stop. One could stop. They could both continue in the same direction. They could both continue bouncing in opposite directions as I've drawn it here. So all of those outcomes are possible, as you will see. But this is the one that I'll just draw just just to have something to draw, at least at first. So let me go back to why I want this surface to be horizontal. Surface to be horizontal, that means the normal force and the force of gravity cancel, right? And the force of kinetic friction is approximately 0 if it's frictionless, right? Or I guess I should say exactly 0 if it's frictionless. And so what that means is that putting these guys on this surface means that the net external force on these guys is 0. So there's nothing from the outside environment that's going to come in and disturb A and B. The only thing that's going to affect A and B is their collision with each other, right? Does that make sense? So I'm not saying A just continues on at a constant speed in a straight line, according to Newton's first law, because it doesn't feel a net external force. When I say external, what I mean is from the outside environment, right? So outside environment, it's still going to collide with B. So I'm kind of thinking of this system, it's like in a bubble. There's nothing that's coming and affecting the system from outside the bubble, but of course, if you have another member inside the bubble, then you're going to get slammed into. So let's take a look. The net force on A is of course going to not be 0 because B hits it. And what that means is that the momentum of A will change. Right? A is going to feel a collision from B. It's going to exert a net force on A, and A's momentum is going to change as a result, right? You can see that here. If it changes, if it bounces off in the opposite direction, that's a change, right? Even if it was going the same speed, momentum is a vector. So if it goes from point to the right to the left, that's a change. You can, of course, use the same logic on B. The net force on B is not 0 because A hits it. And therefore, the momentum of B will change. Oh, I'm saying, it's weird. I'm saying delta changes? That doesn't make sense. I should say it's either that the momentum changes, the delta is not 0. Let's try to make some consistent sense. Okay. So both of their momentums are going to change during the collision. I'm not going to expect that each of their individual momenta is going to be the same afterwards as before. Right? But we know that the force of collision, that's a Newton's third law action-reaction pair, right? We can say that the force on A from B is equal and opposite to the force that B experiences from A, right? So this is just Newton's third law. And remember, I've tried to set this up in such a way that that's the only relevant force involved, right? Is this collision force. There are no outside things like friction or whatever, you know, normal force and gravity not canceling because it's an incline. I've tried to take out anything that comes from outside. This is the collision force. I guess I should label it collision force. So here's what I'm going to do. I'm going to plug in. Remember, the first thing is what it's on, right? So it's on A from B, on B from A. So I'll put in, looks like this. So I'm using my formula. Let me ask you this. How do the times relate? How does the time that A feels a force and the time that B feels a force, how do they relate? same, right? One can't touch one longer than the other touches it, right? It's a mutual thing, right? Collision time. So these are the same time. So that's just the time that they exert forces on each other. Let me go ahead and put in the mass of A, velocity of A. Over here, same thing. So here's where we have a crossroads where we could go one way to where we've been before, or we could go another way and get something interesting and new. Now, is the mass of A constant during the collision? Yeah, it comes out having the same mass as it came having in, right? Is the mass of B the same before and after? Yeah, so we could factor out the mass of A from the delta, the mass of B from the delta, and then of course what do we get? We just talked about this, delta V over delta T is acceleration, so we get this. Mass of acceleration, M, you get this, right? That's not new, that's not exciting, right? In fact, you did this problem. You had it on your first exam. Remember that problem? I think you had like a parent and a child on the ice and they pushed across against each other. And you could, if you know the mass and acceleration of one and the mass of the other, you can get the other's acceleration, right? Do you maybe remember that? Okay. Good. I think it was homework 5, end of homework 5-ish. So one of the things we of course discovered is that they're not obligated to have the same acceleration, right? If a child and a parent push off each other, the child's going to have a bigger acceleration because why? Smaller mass, right? All right. So that's the old stuff, old news. I'm going to not factor out the mass. I'm going to do something else. Check this out. First of all, if the time is the same, let me just cancel it. Okay? And then I'm going to write out my deltas in full. So I'm going to have MA BA final minus MA BA initial on that side. And over here, I have a minus, and then I had to do the same thing. Now, what am I really having here? What I'm having here is delta P for A is equal and opposite to the delta P for B. What I'm saying is that they have equal and opposite momentum changes. So, we said that A definitely has a momentum change, right? We said that A is going to have its momentum change because it feels a force from B. We said that B's momentum definitely changes because B definitely feels a force from A, but they have equal and opposite traits, which means that whatever momentum is given to one is taken from the other. So what is going to be true of the entire momentum of the system if it's just traded from one to the other? It's going to be no change for the system as a whole. In fact, if I take this equation and I rearrange and I put all the initials on one side and the finals on the other, here's what I find. Well, let me just write it like this. What I find is that this is the entire system momentum. And the entire system momentum, it's all still there at the end. Because whatever momentum change was caused by one on the other is made up for in that other one. They trade momentum amongst each other. So, here's a way to visualize this. We again have two accounts. Only now these two accounts are the momentum of one and the momentum of the other. Now here you have to stretch the bank account analogy a little too far, right? These are vectors, right? So these are vector quantities. The internal collision forces will take from one and put to the other, but the total is the same. So if I draw myself a little bubble here, this is the total system momentum. That is constant. So when you have a system where there's some internal interactions, what they're going to do is they're going to take momentum from one participant in that collision, give it to the other, but the total remains the same. The only thing that you have to make sure is that there is no net external force, because external force can, of course, bring momentum in collectively or take it out. So what we're trying to do is we're trying to shield this system from any external influences. Any internal collision forces just take momentum from one and give it to the other. But we can expect that the total is going to be the same. And here's why this approach is so nice. Because just like in the energy method, right? In the energy method, we cease to care about the individual works because they just trade it back and forth between one energy form and the other. We just try to make sure that KE plus PE was all there. We don't care about the number of transactions that it had to go back and forth. We just make sure KE plus PE is accounted for, right? Same thing here. There can be some immensely complicated internal collision forces which we couldn't care less about, because we know that the only thing those internal collision forces are going to do are going to take momentum from one member of the system and give it to another. The total is still going to be all there. So what we can do then, if for instance we know the masses and we know 3 out of the 4 velocities, we can get the 4th velocity very quickly, not having any idea about the internal nature of the collision forces. We don't need to know how many newtons it was. We don't need to know how many seconds it lasted. It could be quite complicated. There could be numerous collisions. We don't care. We simply make sure that the momentum that's in the system to start with is all there at the end. So I'll do some example problems on this next time.